Good morning, everyone. I want to welcome you to another statistical class. Of course, today, the focus is going to be on density-based spatial clustering of application with noise that we also abbreviate as DBSCAN. Okay, so in the outline, I'm going to have a review on K-means, K-middoid, and hierarchical clustering, so that you'll be able to see the connection between those type of clustering and the one we want to do today that we'll call the density base. And of course, I'm going to walk you through the algorithmic process, applications, evaluation method, and limitations of the density base clustering approach. Okay, so let me say this. We find ourselves in a world where we believe objects cannot belong to the same category or group, and because of that, we actually want to have a way to group, to partition. And of course, if I'm referring to, add way of clustering in such a way that we can only, in a particular object can only be in one cluster, and where there's no overlapping. Of course, we make use of K-means, K-middoid, and the hierarchical or clustering. I told you why we move from K-mean to K-middoid, because of the fact that there's possibility of outlier. And with K-middoid, of course, you're not going to make use of a centroid, which is based on the mean. You're actually going to make use of a particular data point. And what keep you going is because you're able to save the cost, after swapping process. And of course, if you really want to understand the relationship between clusters, okay, of course, the hierarchical clustering comes in. You know the difference between hierarchical clustering and K-means and K-middoid. The K-means and K-middoid, they actually have objective function, but the hierarchical clustering does not have any objective function, but instead we use linkage criteria. If you look at the current assignment that I gave, assignment 3, where I asked you to figure how, which of the linkage is going to work. Is it going to be a single linkage or complete linkage or average linkage or what, stuff like that. So that is on the, with the hierarchical clustering, of course, you're actually going to generate an hierarchical tree. But let me tell you this. When you take a look at the K-means, K-middoid, and hierarchical clustering, we realize that they collectively have limitations. Why do we normally consider other approach? Why do we consider other method? It's because of the fact that we have limitations in a particular approach, and that is the reason why we want to consider other approach. So the limitation with the K-means, K-middoid, and the hierarchical clustering is, the three of them have to do with the spherical shapes. The shape of the clusters have to be spherical. Okay, the situation where you have irregular shapes. Okay, the moment the shape of the cluster is not spherical, okay, none of that is appropriate for use, whether K-means, K-middoid, or the hierarchical clustering. And because of that, in a situation whereby the hierarchical, the cluster shape is arbitrary, it's not spherical, then we actually need to consider what I call a density-based way of clustering. When I talk about density-based way of clustering, it means if I want to classify objects into cluster. So those that can be in a cluster are those ones that have high density. And the low density one will not be part of the cluster, and they're going to be regarded as an outliers. So I welcome you to, DBS CAN, an acronym for a density-based clustering algorithm. This was actually introduced in 1996. Incidentally, I graduated from high school in 1996. How many years ago? Oh my God, that's so many years ago. So that was introduced, by Esther and et al. Esther et al. And of course, the idea behind this clustering is, can we have a way to also do clustering based on irregular shapes? Okay, irregular shapes, or arbitrary shape that is other than spherical. Okay, so that's exactly what we mean. So so that was why I say it can discover cluster of arbitrary shape, okay, robust to outliers, and no dependency on distance metric. If you take a look at k-means, k-median, and the like, the result you get depends on the metric distance. You remember the metric distance, the Euclidean distance, the Manhattan distance, and so on like that. So, but this doesn't depend on that. And the belief here is, this actually define cluster as a continuous region of high density. Okay, this approach, okay, define clusters as continuous, okay, regions of high density. Okay, and this can also help us to identify some outliers. Okay, and let me tell you this, let me prepare your mind. Let's say, for instance, you work with police, and you actually want to identify crime hotspots. I'm going to say that again. You want to identify crime hotspots in a big city. Okay, in a big city. Okay, so what we need to do using this approach, okay, is actually to cluster, to identify locations, okay, with such crime incident, okay, and not only that, we believe that those locations they have high density. They're actually going to be in a cluster. And do you know at times we could have some isolated events? Okay, maybe outside those locations, okay, crime occur, but crime don't just occur frequently in the particular area. So that could be referred to as an isolated event that we're going to call outlier. So this particular clustering algorithm will enable us to detect some abnormal, we call them anomaly, the outlier. Okay. And let me tell you this, when I was talking about arbitrary shape, at times crime may occur in an irregular geographical location. If crime occur in an irregular geographical location, the k-means, the k-midoi, the hierarchical clustering will not be able to capture that. What do I mean by irregular location? Maybe I'm talking about a crime that occur in a street network or a riverside. Okay, a riverside. That's not gonna be part of it's not gonna be spherical in shape. Okay. Now, how does it work? There are two major parameters when it comes to the density base way of clustering. Number one, you need to identify the minimum neighborhood distance. Before I can classify locations within a major city, okay, to be hotspots for crime, okay, then I need a threshold that I call EPS epsilon, which is minimal neighborhood distance that I'm actually going to use to classify those locations into the same cluster. Okay, so that needs to be known. Okay, now another parameter is what is the minimum number of data points? When I say data point here, I mean locations where the crime occur, maybe the burglary or whatever occur. Okay, now we have minimum samples, mean the minimum number of data point we want in a neighborhood, okay, to define a cluster. Does that make sense to everyone? So these are two major parameters. And let me tell you this. One of the limitation of this method, situation, cities, they have very density of crime, right? Cities have very density of crime, right? If you use the same neighborhood distance across city, then you're going to be wrong. And that is why, DBS, that is one of the limitation of DBS. Reason why we're going to consider what we want to do on Friday that will call the general, the GMN, general mixture model. Okay, you can see limitation of one will lead us to exploring the other. Okay, so I said for each instance, the algorithm counts how many instances are located within a small distance epsilon from it, which means a researcher will be the one that will set a threshold on the minimum distance you're going to tolerate between objects before they can be classified into the same cluster. Does that make sense? The epsilon must not be so large and must not be so small. Otherwise, you are likely going to classify some objects as outliers. We don't want, and maybe they are not outliers. Does that make sense? Maybe something occur in an area, you just say, oh, that's an isolated event. What if it is not? Okay, now, and the region is called, we call that epsilon neighborhood, which is that epsilon neighborhood. Okay, it means that is a minimal distance that you're going to tolerate. Now, I want to go further demonstrating this. We got some elements that we use in describing density base or clustering application of noise. There's something that we call core points. Okay, and the core point, you actually want to consider, the minimum sample point. Okay, like the minimum numbers of neighborhood a given point you have in order to be classified as a core point. Oh, you are a core point. Okay, can we know the minimum numbers of neighborhoods you're going to have to get classified? I'm going to show you visually. We also have a border point, okay, the one at the border. The one at the border is going to be far away. It's like where you're traveling to. I remember when I was driving to North Dakota, okay, and I get to I get to the border. What happened at the border is far away from major city, the state you're actually driving away from. So the border points, okay, are within the epsilon, that's minimum neighborhood distance that I said, you're actually going to set, but do not contain minimum number of neighbors. Okay, it doesn't have minimum numbers of neighbors to be classified, to be considered a cluster. Then we also have a noise. Okay, now I need you to take a look at what I'm going to be showing you now. Please pay attention. Okay, point A, when you take a look at point A, okay, and every other red point, okay, that point A is a core point. Okay, and why is it a core point? Is because it actually have the minimum number of cluster point to be classified as a cluster. Okay, and what is the minimum? It must contain at least 4 points. Please take notes. At least 4. At least 4. I'm going to say that again. I said point A and other red point, we call them core points. Okay, and I said because the area surrounding these points, okay, in that neighborhood radius, that minimum distance that contain at least 4 points, including the point itself, including point A. Does that make sense? Now, let's talk about the yellow. Oh my God, let's look at the yellow right now. The B and C, those are like the border points. You remember when you have a city, right? When you have a state, okay, be bounded, gonna share boundary with a particular state, maybe in the east, or share another boundary with another state, maybe in the west or something. So if you take a look at the B and C right now, okay, we actually refer to them as a non-core point. They are not core points. Okay, they are not. They are the border. Okay, so because of that, I'm actually say they are the border point. They are not core point. Even though they are within the radius you set, but they do not have minimum numbers of neighbors to be classified as a cluster. Does that make sense to everyone? Okay, now you understand the red one, you understand the yellow one. Can we talk about the blue one? Oh my God, look at the blue one. That's an outlier. Okay, that's actually far away. Okay, we call it an outlier, call it an anomaly. Okay, that could refer to as an isolated event that we talk about. Does that make sense? Okay, now we are partitioning locations in a particular city. We actually want to detect hotspots, for crime. Okay, and as you can see, we got some isolated events in blue, and you see where crime events are densely concentrated, the red one, the core point, and you can also identify the border, okay, also captured in the cluster, and take a look at the other one that is also far away. Now, if you want to let's say you want to run the algorithm with DBSCN using any statistical software, R, Python, and so on like that, we want to tell you the time it takes to run. Okay, here the worst case runtime scenario is n squared. What is n squared? N, the number of, you're actually going to have n by n matrix, right? The dissimilarity matrix. Okay, so there will be n multiplied by n times, depending on the number of your observation. Okay, and if you are indexing if an index instruction is used, there's going to be log n. Then the overall average is n log n. Just sort of trying to tell you to prepare your mind about the running time, so that it doesn't look as if you're going to wait forever. Now take a look at oh my God, I just want to show you the difference between spherical clusters and the arbitrary one. If you look at the one, if you give me 1 second, if you take a look at all these ones, those are spherical. Okay, K means K-medoid, hierarchical structure, clustering. They're actually going to do a great job, in identifying that. Okay, because they have the strength in, working with the spherical shapes. But at times we could have some arbitrary shapes like this guy here. Okay, So K means K-medoid may not be able to capture that. And that's why we need a density-based way of clustering. Now, take a look at this another example right now. Oh my God. You know, on a given set of data point, okay, if you use K-means, can you see what you have here? Okay, that is not a very good identification. You can see there's a green here, there's a green here, there's a green there. Okay, so this is not normal, this is not proper at all, because a K-means will not be able to identify the shape, the cluster shape correctly, because it's arbitrary, it's not spherical. But look at the DBSAN, look at that. Look at that. You can see red in one side, green, and blue. Take a look at that. Any question on this? Any question? You're good, right? Okay. Now, I need you to pay attention to this. There's so many clusters here. Okay. K-means is not going to do a great job if this is the original shape of clusters in data set. Can somebody tell me how many clusters can you see? How many? How many clusters? Go ahead. How many? That's kind of dicey, right? Okay, just say one. Just 3, 4, 5. Just one. 4. Any other person? How many clusters do you see? Go ahead. You say 5? Okay. It's actually 5. And you also close. Thank you for sharing. Now, this is one. This is another one. You have the straight line. You have the one that looks like a straight line. That's another one. Then this guy here. Do you see that? So, but using the K-means or K-medoid, because we are working with, we have arbitrary shape now. Okay. We may not be able to, it may not be able to capture that. When you take a look at this one, that's what we call two ovals. Two ovals. When you have a cycle, you have another cycle inside a cycle, that is what we call ovals. O-V-A-L-E-S. Two ovals. Then this one, we call that two linear clusters. A cluster can be linear, a straight line, two linear. And this one, a compact cluster. Does that make sense? So making 5. Okay, now you understand. You know what I want to do now? We want to go into R. Want to go into software. Okay, how do we implement this in R? We need to load some packages, just like what we did in the case. And you know what we want to do now? We want to simulate, okay? We want to simulate multiple shapes, like different kind of shapes. And we want to compare the performance of the algorithm with K-means and the like. Okay? Now, this is the code. Now, we set seed. Don't forget we're simulating. We want to have the same values for reproducibility. Now, you know what I want to do now? I already know in my mind the shape to be arbitrary. I simulated that. I deliberately simulated arbitrary shapes, not spherical. And I decided to can I test the performance of K-means to be able to tell the world that K-means is not capable of doing that. So, you know why n start equal to 25? I told you the other time. Okay, the random assignment. Okay, the random run wanted to be 25. It said between 25 and 50. And the reason for that, because of the approach of K-means, okay, because of the cluster assignment and the centroid it induce null convexity into the function, and because of that, there's possibility of getting trapped in a local minimum, and that's why your end start, should be at least 25. Does that make sense? Okay. Now, we now want to draw the picture and see for ourselves. Let's draw the picture right now. Can you see that? The K-mean is going to give us this, but you can see the green, you can see cluster 2, right? K-mean is trying to say this guy here and this guy here, they are in the same cluster, which is not correct. It's not. Does that make sense? So this is to show the world that, K-means is not appropriate for situation where we have arbitrary shape, not spherical shape. Not only K-means, K-midoi too. Okay, now because of that, I'm going to show you different kind of shape we could have, cluster shape. Take a look at that. Could be down, 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 different kind of shapes. Let's look at the advantages of this. Okay, unlike K-means, this algorithm does not require you specifying the number of clusters ahead. In the K-means, you normally specify the numbers of clusters ahead of time. Okay, and of course, this particular algorithm can find any shape at all. Okay, then it's very, very useful in identify outliers. Okay, now let's go into the R code. If you actually want to load, you need to load some packages. Okay, if you really want to run this in R, FPC and DBSAN, that is the name of the algorithm. Now, if you take a look at this right now, you're going to write this. This is a function for that, your data. The two parameter, EPS, that's epsilon, the minimum distance between two points before they can be classified into the same cluster. And not only that, the minimum point, I told you, the minimum point to be classified into a cluster has to be at least 4. Here now, I'm using 5. I'm okay. Minimum, at least 4. Now, mean point equal to 5. Scale equal to force. When scale equal to force, maybe they want to scale your data. Okay. Now method, hybrid, raw, distribution. Okay. I think I just give you the definition again, like in case you want to know, here in this function, what data represent, what EPS, what minimum point, what hybrid. Take a look at that. Your data is your data matrix. Okay, the EPS, the reachability maximum distance, that I call the neighborhood distance. Then the minimum point, the scale, the method. The method, we got 3, DIST, treat the data as a distance matrix, or treat the data as a raw data or hybrid. Expect or raw, but also can also calculate the partial, matrices. Now, you know what I want to do now? I want to generate shapes, and I want to test performance of DB. And the shapes I'm generating, I know the shape myself. They are arbitrary shapes. I've already tested the performance of K-means. K-means perform poorly in identification of clusters. But what do I want to do right now? I'm actually want to generate my data myself, the shape myself. Okay. Now, doing that, I load the package. I set a seed. Then I indicate the EPS. Don't forget the EPS, the minimum distance here is 0.15, and the minimum number of points to be classified 5. Don't forget I said at least 4. Okay. And I make the plot after running, the DBSAN. Oh my God, look at that. Compare this now with what the K means actually provided. And that's how we know that this is actually fantastic when it comes to arbitrary shapes. You know, anything that is not having any color here, they're actually going to be classified as outliers. Any point outside all of that, all the five. And that's why very visible to identify outliers, okay, using that. So it can actually be seen here that, the density-based algorithm perform better, okay, because it identified the clusters correctly. The k-means did not identify the cluster correctly. Okay, now, you know what I want to do here? I actually want an outlier to be visible, okay? And take a look at this now, the new shape, or the black one, or the black dot are outliers. If you are talking about crime in major city, where you actually have, you've grouped into 5 locations within a city, okay, outside those 5 locations where you identify hotspots, then the crime events in outside those 5 clusters, they are isolated events that we can call outliers. And that's why when I see police, I respect what they do, because they don't just go out. Some of them are statisticians too, or they have statisticians working for them that will tell them where to go. Does that make sense? Okay. Now, the next thing is to print DB. If you take a look at what I have here, you can see DB, right? Okay. And let me see. You can see here, I said DB less than negative FPC, indicating that. So if I actually want to have access to that, I'll be able to know the number of, take a look at that. I need you to, please pay attention now. Pay attention now. I need you to pay attention now. If you take a look at what I have now, okay, the total number of points in general, 1,100. Minimum numbers of points to be classified as a cluster 5. The neighborhood distance, the minimum distance, 0.15. So it's actually going to tell you what is it in each cluster, what is going to be the numbers of the border point, the say, and the total. Now, is 0 here is for the outlier. Does that make sense? Did I tell you the numbers of outlier? Then 1, 2, 3, 4, 5 represent cluster 1, cluster 2, cluster 3, cluster 4, cluster 5, cluster 0 is outlier. So like I said, that correspond. Okay, I said in the table, the cluster, the column names are cluster number 0, 1, 2, 3, 4, 5. The 0 is, cluster 0 is always outlier with the DBSAN. Okay, now I've walked you to, now another thing now. How do we decide on the optimality? For instance, there are 2 parameters using DBSAN. How do we decide on the neighborhood distance? How do we decide? The neighborhood distance that will correspond to a particular number of points, even I know the minimum number of points is going to be 4, but how do I arrive at the minimum distance? Okay, and also I said that is to calculate the average of the distances of every point to its nearest k neighbors. Okay, so the value of k will be specified by the user and correspond to the minimum point. Okay, so then next, this k distance are plotted in an ascending order. And why we do that in ascending order is to determine the new. You remember the other time when we're talking about K-means, K-midoid, hierarchical, we talk about EBO. You know EBO, right? We talk about gap statistic and so on like that. But right now, it's new, Knee. So a new that corresponds to a threshold, okay, where you have a sharp chain occur along the K distance curve. What is the arrow code for this? Please, I need you to pay attention. Okay, I'm going to be DBSAN, KNNDL, this plot, DF. DF is your data, K equal to 5. Then by the time you do that, you're actually going to have this. This is going to give you a reasonable, which means from the data set, you are not going to be the one that will decide that, the minimum distance, because if we have set of data, okay, and different researchers are working on set of data, your minimal distance may be different from mine. And that is the reason why we should have an optimal way to figure it out from the data set using this. You know what this guy is suggesting now? Look at the dotted line. Oh my God, the dotted line may be around 0.15. That was why we used 0.15 the other time. This actually came from the data. Okay? We don't want to use principle of subjectivism because of difference in ideology. We're likely going to have different values for the EPS. And the values of the EPS you choose, the neighborhood distance you choose matters. Okay, I want to go into real life application now on data. Like, I don't want to talk about simulated data anymore. In statistical analysis, I know some of you are familiar with iris data. Has anybody about iris data? Oh, okay, thank you so much. You know, in iris data, we have a different kind of species. Maybe there are 4 of them. Okay, there are 4 of them. Okay, talking about sepal length, this, that. So when you take a look at, that was why we have, when you load this, you know, now you're going to have access to iris data. Okay, 1 to 4, because there are like 4, variables. Okay, we want to use. Now, the first thing I want to start with, the very first thing I want to start with here is, can we decide on what the EPS is going to be? Does that make sense? The minimum neighborhood distance, the epsilon that I talked about. Okay. Now, after that, we write this code. The EPS now equal to 0.4. How do I know that? Maybe I determine that from the data set. Okay. And I indicated my minimum point. Let me tell you, the minimum has to be 4. You can have more than 4. Okay. Now, when you do that, you now want to see the picture that's going to come out using the the DBSAN on iris data. Okay. And let me tell you this, naturally, that iris data actually have 4 categories. The best way to do clustering, if you really want to tell whether your clustering algorithm is doing a great job, I think if you know the classification in advance before you use it, it's just like maybe I ate burger in the morning, and I say, okay, before I'm going to ask this guy, I'm going to ask this, before I'm going to ask this guy what I'm going to eat tomorrow, I'm going to say, okay, can you tell me what I ate in the morning? Because I know what I ate in the morning, but I don't know what I'm going to eat tomorrow. So if this guy can confirm to me, oh, you ate burgers, and if truly I ate burgers, I will actually rely on this guy. That is the same thing here. We already know the classification of this data set, but we just want to try and use DBS. This is what you're going to come out. Take a look at that. That is, what do you see? This is trying to tell me right now. There are some outlier in this data set. You see the black point, right? I told you this one now. They are actually, the black points are the outliers. One of the significance of this approach, is that to enable us to detect outlier. Okay. Now, I said, now let's come back to limitation. Judge Box said, and I quote, all modules are wrong, but some are useful. Do you know why Judge Box said that? Because he said, well, if you ask me a question, how true is a module? If you mean complete true, the module is not true. Why is it that module is not true? Whatever module we use, whatever algorithm, it's because they have assumptions. All modules have assumptions. And assumptions translate into limitations. And that is the reason why we need to consider another module. You can say we started from K-means, that's limitation. We go to K-midpoint. Then we go from there now, situation where we are no longer having spherical shape. We came all the way to the density-based approach. But you know what? The density-based approach has limitation too. And that is the reason why we want to consider the generalized mixture model that we want to do on Friday. Now, what is it? This guy has approach with high dimensional data when you have so many features. For instance, let me use crime. Crime occur, right, in a particular city or location within a city, and that very crime, you have so many variables that you collect: the time of the crime, the demographic, the race of the person, and so on like that. And you have so many features. Even though the shape of the clusters are going to be arbitrary, the density base will actually struggle with that. Does that make sense? Now, and I said this is because the minimum sample EPS combination can not be chosen appropriately for all clusters in that regard. And I said DBSAN cannot cluster data set where with similar density when there's a significant overlap in the distribution. Now, don't forget, significant overlap is that situation whereby a particular member belong to this cluster and belong to another cluster that cannot be captured by DBSAN, because DBSAN and K-means, K-midpoint, the hierarchical clustering, they are all classified under partitioning clustering that I call hard clustering, where when you partition members into cluster, you can only belong to one cluster. Do you know at times when crime occur, maybe a crime of robbery occur, okay, and that robbery involve violence. Look at that. The robbery now involve violence. DBS may not be able to capture that. What are we going to capture that overlapping one? That is the generalized mixture model that we're going to do on Friday. Is there any question before I go today? Do you enjoy this class today? If you're enjoying the class, can I see your hands up? Oh, okay. Thank you so much. But you know what? You know what? If you know you don't understand, meet with me during my office hour. My office hour now, Tuesday 10 to 12, Thursday 10 to 12. 2 days that I commit to office hour. You can be anywhere in the world to attend my office hour because it's going to be on Zoom. Okay? It's going to be on Zoom. Make sure you all stay safe and have a lovely day. Bye for now, everyone. Yeah, Tuesday and Thursday 10 to 12. Yeah. Yeah, it's the same that is the Zoom link on the syllabus. Yeah, you're welcome. Yeah. Okay, go ahead. Oh, oh, no, no, no. If you come here, this is it. Because from here it started, oh, it's going up and down, but we don't want so many. So I'm gonna say two. Mm-hmm. You know, we got different kind of data, so yeah, that's right. Yeah, yeah. But this one here is like it's now increasing again when the cluster is here. So maybe because there's some data that behave abnormally. So but based on what you see here, you can report case for two for that's okay. No problem. Okay. Actually, so now I'm seeing that that is possible that happens. So, yeah. Okay. And then you do scale your data before you yeah, at time yeah, we scale okay. At times we don't scale, but in the yeah. gaming, the one we've done before, we scale a lot. We gotta scale. You know why okay. we scale? Want to normalize the data? Yeah. Normalizing like, the feature may have different view. Yeah. So how do I bring them into the same yeah. Okay. Because the reason I was asking is the hierarchy. Yeah. I think you said one of them was equal to both. Yeah. But why do you not standardize them? Because we're talking about domestic. I'm sorry, deterministic. It doesn't have objective function. Yeah. So it doesn't matter. It doesn't matter because those k-means and k-meter as objective function, I would say they shouldn't be poorly scaled. That was why the scale. Oh. Does that make sense? Wait, sorry, repeat. Okay, we said um K means K meter has some non-conversing. Yeah. Okay. Now, because of that, what could lead to all of that is because it's poorly scaled. We have an objective function that is poorly scaled. And to get out of that, one of the things we can do is to standardize, is to scale. Okay. But the hierarchical doesn't have objective function. Okay. It's just based on sense now? Yeah. So yeah. But then hierarchy just based on your distance of the distance. The distance. That's why the hierarchical trying to minimize the total sum of the similarity. That's all it minimizes. But the K-mean doesn't do that. Right. That talk about the square of the division around around the center. Yeah, that's true. You can say they are not the same, like even though they have the objective function. Okay. Okay, so for hierarchy, so I have to keep it as not scale. Yeah, you can keep it as not scale. And at times you can also look, you know what I need to do now? I need to do the research. Scale, don't scale. Send it to me about the result I got. Okay. Yeah, that's a research. Yeah, all right, I'll do that. You're welcome. How are you? You well. Okay. I just had a question. So, is there any way I can take that? I didn't see that. No, but even though I'm going to take it out, I think that means yeah, I'm flexible. Because I know some of the students in sports have some things. And then that's the thing. That's the thing. Yeah, yeah, right. Yep. Yep. I can't find so it's kind of small. So which means that is that. So what I'm going to write that yeah, I think I did that. Yes, I thought that I like that side of points. There is no return. You can try because okay, you know what, can you make it out? Yeah, okay. You don't need to call me person is on. Oh, yeah, that's why I did online. So you can be anywhere in the world. Yeah. Yeah. Yeah, the four. Let me see. Yeah, the four method. The do payments. Oh, okay. So it's payment and it's pay me back for the four.